Hello and welcome to New Planet School. Today we're doing a video in the series What Is It? And in particular we're going to look at trigonometry and ask the question, what is trigonometry? Why would I want to learn trigonometry? Why would this be useful to me? Why would this be interesting to me? And it's good to keep this in mind as you learn trigonometry, because you can get down into the details of how solving homework problems or whatever it is that you're doing, and forget that this is actually a really interesting and important topic. So that's what we're going to cover today. We're not going to learn a lot of trigonometry. We're just going to learn about what it is and why we would want to learn about this topic. So what is it? So the word trigonometry comes from these two Greek words here that mean triangle and measure. Obviously, you see the word tri here, which refers to something with a 3, like triad, triangle, tricycle, anything with 3. And you see the word here, met, which has you think of things like the metric system or a meter, and you see those word roots. And so that's what we want to do here, is we want to look at things that have 3 sides like this. And we want to think about making measurements of things like this. Like, for example, how are all these angles related to each other? And how are the angles related to, for example, the lengths of the sides and so forth? And so that's really all that trigonometry is about. It's actually a fairly simple topic. Now, why did people start studying this? People started studying this a very long time ago. Most of the people who were important in this, like Euclid, Pythagoras, and Hipparchus, all lived a few hundred BC. But today we consider that the father of trigonometry is Hipparchus, because he's the one who really looked up at the heavens and the stars and the planets and tried to make sense of it, and realized that there was something important there, very concretely, that trigonometry was important, and tried to understand what the trigonometric functions were and tabulate them and put them to actual practical use of making sense of the world around him. So later people came along and applied it to, continued to apply it in science and understanding the planetary motion, the movement of the stars, and our place in the universe, but also from a practical perspective, understanding things like navigation and mapping. What is the shape of the continents? How do you make your way across the ocean to discover new continents and so forth, and not get lost? And so triangles played a very huge practical use in the discovery and understanding of just the planet that we live on. So, but from your perspective, probably learning math right now, you've probably learned things in math about numbers, adding numbers, multiplying numbers, arithmetic, fractions, decimals, probably have maybe taken a class in algebra and learned about functions and how to graph those functions and so forth. And all of these things turn out to be really important in trigonometry, which is why you want to make sure you understand those topics pretty well, because you want to focus on on trigonometry and not those topics. So once you have those down, you're ready to cross the bridge into what's really a new area of math for you, which is the study of, as we said, triangles. But what's most important about this, and what's fundamentally new, is that this object right here is a shape. And that's really what's different about trigonometry. If you go back over here, numbers, fractions, algebra, functions, graphing, none of these particularly have to do with what are the properties of a shape. And what trigonometry is your first window into the mathematics of shapes. And that's why it's a little bit new. And once you realize that that's what it is, it's the mathematics of the relationships of a shape, it's sort of easy to understand why you're doing what you're doing. And as we'll see in this video, why understanding the mathematics of shapes is actually really important. Now, trigonometry itself is a sort of a small part of mathematics in a sense, because what it really is a subset of a larger field of mathematics that once you learn trigonometry, then you cross another bridge to a bigger area of what's called geometry. And so, like, for example, you can see here's a triangle, right here, also 3 sides, but it's on this curved surface, where over here we're going to look at 3-sided objects, always in a flat surface like the screen that you're looking at. So it's really worth understanding these shapes and how to do the mathematics of shapes just as a general topic before you move on to learn about more sophisticated mathematical properties of shapes. So totally worth learning trigonometry and understanding it well, because it will be very useful down the road for you. So what do we do in trigonometry? We have a shape. We have a shape like this one. And it's a triangle, obviously, and it has 3 sides that I've labeled here A, B, C. Those are the lengths of those sides. And a long time ago, even before Hipparchus, Pythagoras looked at this shape, and he noticed some interesting things about it. He said, if there's a right angle right here, a right angle, which means that these 2 lines are perpendicular, that means that this type of triangle is called a right triangle. He was able to come up with a rule, and the rule he came up with said the following. If I put a square here, which has length A here, obviously, and length A here, it has an area A squared, because that's the area of a square. If I put another square here with length B here, then this will have area B squared. And if you put another square here and put side C here, this will have area C squared, and therefore you get the Pythagorean theorem, which is written here, A squared plus B squared equals C squared. And this is the type of a rule that we came up with, that any right triangle will always obey this rule. It doesn't matter what it looks like. It could look like this. It could look like that. It doesn't matter. As long as there's a right triangle, the longest side is C, the other ones are A and B, then they're going to always obey this rule. And he proved that for all of them, all of the triangles that are right triangles. And just as a side note for later, the side across from C has a special name. The side across from the right angle, which has length C, that is called the hypotenuse. And so sometimes you'll see me label it with an H for hypotenuse. And so that's another name that you see in trigonometry for the longest side that's across from the right angle. So that's an example of a rule. Let's look at a different rule. Here's another rule for similar triangles. So these 2 triangles, as you can see, are similar. They both have right angles, so they're both right triangles. And what you can do is, if this angle equals this angle, then you can prove that the ratio of the 2 sides over here, the ratio of A to B, which is this ratio, is equal to the ratio of little a to little b, no matter what. And so this is basically just a scaled up version of this, and this is a scaled down version of that. And so any property that we know of this triangle, we immediately know a lot of properties of this triangle. And so that's an example of how a rule that always holds, and you can use that to your advantage. So let's see precisely how we can use that to our advantage. Suppose one day you're out walking in the desert, and you come across a forest of saguaro cacti, and you realize these are enormous. These cacti are really large, and you look at it and you go, I wonder how high that is. And the first thought that you might have is, maybe I'll climb to the top and take a tape measure with me. And then you walk over close and you see all the little spines in it. You decide probably climbing this thing's a bad idea. So how can I use some rules that I've developed for triangles to figure out how tall this is? Okay, so one thing you can do is you can measure the distance along the ground very easily. And you can stand over here, our friend over here is standing over here, and you can look up and you can see the top of that saguaro cactus, and you can see that this forms a triangle. Okay, well, if you can form that triangle, you can form other triangles that are similar to it. In fact, one of the things you can do is you can make one of the triangles the same height as you are. There's no reason you can't pick one. There's a whole bunch of similar triangles, and so let's pick that one. And to make sure that they're similar, what we'll do is we'll make sure that they all line up over here and they have all the same angles. They're all right triangles with the same angle. They're all similar triangles. So having verified that we have similar triangles, we just simply measure the angle. So we go in, we're over here, we measure this angle here, let's say we call it theta. It's the same for all of the triangles. We make a little triangle, step 2, with the same shape. That's this one right here that we have that has the same height as we have. And we measure the lengths of the sides. So obviously here we can measure this length easily. We've already done that. We put a ruler over here in case we didn't know how tall we were. We now know that length. And then we just scale the lengths to find the height of the saguaro. So for example, we use this relationship. The height of the cactus is the distance on the ground times these values. So I know the height of this triangle, which goes here. I know the base of that triangle, that goes there. I multiply that by the distance on the ground, which is this distance right here, and that goes in here because they're similar triangles. Then I therefore know what I'm after is I know the height of the cactus, and I never even had to get near it. And so that's an example of how using some of the rules that people have developed over the centuries for triangles can help us to do something of practical use. Okay, here's another one that's a little bit more realistic, is surveying. Surveying is a big part of what trigonometry is for. So let's walk through this. Imagine that I'm standing on the side of this lake, Lake Titicaca, looking at it from the Peruvian side. And let's suppose I'm standing right here where this purple circle is, this purple oval, and I want to know how far it is to get over here across the shore. But I'm deathly afraid of water, and I'm not going to swim. It's too cold, and I'm not going to get in a boat because I'm afraid it's going to tip over, but I really would like to know this distance. Well, what I can do is I can be very safe and secure, and I can walk along the shore over here to this other place that's yellow. And again, since I have a ruler with me, I measure this distance. And then you ask yourself, how is knowing this distance from this purple point here, knowing to some other basically random point and knowing this distance there, ever going to help me figure out this distance here? Well, here's what we have two observations to make. The first observation is just to recognize that we have a triangle. This is our triangle. Okay, so we know we're dealing with trigonometry, and we can go use all of the rules that people have developed over the centuries to help us solve this problem. The second thing that we have to be able to know is what these angles are. And so what we do is we know this distance, but we don't know anything about the angles. So suppose we bring in a compass, and while we're standing at these 2 points, so while we're standing over here at this purple point, we measure the angle relative to the perpendicular looking straight out from the path I take to the yellow point. Once I get to the yellow point, and I'm going to call that theta, once I get to the yellow point, I do the same thing. And so I know this is a right triangle, and this is a right triangle because I used my compass to figure it out. And I can measure this angle theta. I can also measure this angle phi. Okay, now I know this, I know this angle, I know this angle, and I know this distance. And as we've noticed, most of the rules we've seen so far involve right triangles, and you might look at this and go, well, it's not a right triangle. What am I going to do? I can't use any of the rules. I know. That's okay. Draw a line down here, and now I have 2 right triangles, one here and one here. So now I can use all the rules of right triangles using these 3 pieces of information. And from these 3 pieces of information, I can then work out, using the rules of trigonometry, exactly what this length is over here. And I'm not going to do it here because the point here isn't to go through a lot of details, but trust me, it can be done. It's fairly easy to do, and in a later video we'll probably go through and actually work this out as a problem. So, but that's the sort of thing we can do. Measure this distance without ever touching the water. Okay, so how is it? Let me give you a little bit of a sketch of how that works. Here's some of the things you can do. There are other rules that we haven't learned so far, is that if this is parallel to this, then this angle equals this, and because this is parallel to this, this angle equals this. And now I'm starting to really narrow down properties of this, and you notice that these two triangles, this triangle on the left shares this side with this triangle, so they're connected. They both share part of this length, and they're also all part of one overall triangle, where all of the angles across here have to be 180. And that is how measurements that you do over here directly are connected with measurements that you make over here. And those are sort of how those rules come in. Okay, so how would you do this in the modern world? Obviously, there's very sophisticated devices that people have created. This is an old picture, but you can see how these things can be automated to make this a very easy thing to do. Okay. Now, trigonometry is about measuring in angles, and we haven't been, I talked a little bit about angles, but not too much. So let's talk a little bit about angles and define some things about the angles that are useful to know. Okay, so the first thing that we know is probably everybody knows about degrees. And so in this picture you can see we have here like a protractor, and you can measure the angle in degrees. Going through here, you have 10 degrees, 20 degrees, 30 degrees, 40 degrees, 45 degrees is halfway up. If we go straight up, that's of course 90 degrees, and then as you go around, there's 180 degrees. I got kind of cut off here. And then if you go around, you have 270, and all the way around 360 degrees. Now, we use this terminology in our normal language of degrees, and so this isn't so confusing. I think probably everybody knows about this. Now, it's related to the concept of slope, and so here's some highway signs from a couple of countries trying to warn people about how steep the road is, and that's another concept, which is slope. And of course, slope is rise over run, and so slope measures the same thing as angle, but it's actually different. In the sense of numerically. So a 10% slope does not correspond to 10 degrees. Those are actually two different ways of measuring the same thing, but they're not numerically the same. 10 degrees and 10% is not the same thing. Another way to do it that we do in trigonometry that's a little bit harder to understand because we don't think about this all the time is we measure angles in units of what are called radians. And the way a radian is defined actually makes doing trigonometry really easy. Even though the slope and measuring in degrees might be more intuitive to us because we use it every day when we're driving down the highway or using a protractor, in trigonometry radians are a lot easier. So what does it mean? What it means is this. Suppose I have a circle and there's some angle here, okay? Now what it is if this angle gets larger, it sweeps a larger arc length here. And what you do is when the arc length that you swept here, which I have as 1, is equal to the radius of the circle, then that angle by definition is 1 radian. So it connects, and it's kind of a neat thing. It connects the angle as you go around to the length as you go around. And so if you know something about how far you went around, then you would know how many radians you went around. And so that's a pretty neat concept that we'll talk about a little bit later. Now, the important thing to do is to keep in mind that there are different ways of measuring slopes or angles in terms of these things. And when you're doing things in trigonometry and you have to use a calculator, be sure that you set your calculator to use the right units, because different calculators, like this scientific calculator, they'll do degrees and radians, but you've got to make sure that you're using the right one. So don't make that mistake. Okay, now let's just look at some examples of engineering. Here's a bridge. This is the bridge we saw earlier. You see triangles everywhere, and this is really important in construction, as we'll see. Here's why. Suppose you have a car that's sitting right here on this bridge, right? And you have this car and it's putting a lot of weight right here. What it'll do is it tends to pull these two down, which then pushes it, a little bit of it will pull in this direction. This one will pull in a little bit of a direction here. And through this triangle you get something very stable, because if this tries to push down, this point can't move because it's connected but through a triangle to this point right here, because they're pushing together. Similarly, what it's going to do is this is getting pulled this way, and it's actually getting pulled this way a little bit down. What it's going to do is it's going to do the opposite of this one, and it's going to actually distribute the weight here, which pushes down, which distributes the weight here, and so forth. And you get this amazing redistribution of forces due to the fact that you've linked all of these triangles together. So it's an amazing thing. It allows you to support things at the ends, but you can support something here and here, but you get this really long span that you can cross. And that's an amazing thing about triangles. You see it in buildings. Same thing, if you need a really large span, you tend to start to use things like triangles everywhere to take the weight of the roof and move it out to the edges where it can be supported by these beams here. So it's using in part the fact that there's an arch, but then you have this triangular so-called truss system underneath it. Here's an example of a roof being for a house. Here's a different type of construction for roof of a house, a little bit more of a pitched roof, but triangles are everywhere to try to redistribute all the forces. And so everything around you that you see, almost every building around you, whoever constructed that building was thinking and using trigonometry. Okay, towers, same thing, just a different type of construction. Not surprising, triangles all over the place to make these things stable and distribute all of the weight. Here's some more towers looking straight up. Here's a really nice looking tower in Tokyo. Triangles everywhere to make really strong objects. People, of course, have known this for a long time. Very stable. Here in Guatemala, here in Egypt, people were using triangles because they knew they could build it and it would stay there, and look how long these have lasted. It's a very stable arrangement. I mentioned surveying earlier, and we went through an example, but today this is very important. Here's an example of using surveying at a construction site. You wouldn't want to accidentally, install the swimming pool and then find out that you did it in someone else's yard. You'd want that to be in your yard. So you wouldn't want to make a mistake, and so there's these fancy electronic devices that allow you to do that. In science, here's an example of geology. Let's use surveying to watch how different points of the earth are moving around and look at the shifting of the plates and how continents actually move, and learn a lot about the planet that we live on. So very, very important. Today, we don't use tools like this. We have high-tech equipment, computers that have everything in them we need. Here's an example of somebody in the military using surveying equipment, all very modern, computer-controlled, high-tech stuff to implement chemistry for practical uses. In industry, obviously, people are using this all the time, looking at angles. Here's an angle. You have this angle. You have this angle, and you're trying to manipulate all of these angles to make sure that the computer is controlling whatever's going on here in a very precise way. Here's another example. You have an angle here you're trying to control, you have an angle here you're trying to control, and you have an angle here you're trying to control. So 3 angles trying to do something very precise here, controlled by the motors over here, all computer controlled. In space, no difference. You can see here, same thing. You're trying to control this angle. You're trying to control this angle. There's a lot of angles on this guy. This angle, this angle, and the astronauts out here trying to get some work done by manipulating this arm that can do a lot of complicated movements. So even at the microscopic level, here's a sugar molecule. And as you can see, the sugar molecule has all these very complicated angles between all of the atoms that make up that molecule. And of course, the properties of sugar are determined by this specific shape and how they can interact with things around them. For example, if the molecules are vibrating, you can get different behaviors if they're vibrating. And of course, as you raise the temperature, there'll be more vibration, and so you can understand how chemistry is changed by raising temperature. In physics, of course, in physics, trigonometry is used all the time. Here's a classic example where you have a projectile that is being launched here. It's under the force of gravity here. It has some initial velocity, and it undergoes some sort of ballistic motion along this trajectory. And we want to know, for example, say, where does it land? Would be, something we might want to know. Or maybe we want to just design a beautiful fountain here with this nice laminar flow of water, which is basically doing exactly this physics experiment. Another example that's exactly the same as this but inverted is a pendulum, where I have gravity acting on this object that's hanging by some angle, and I can look at the different time-dependent forces and accelerations, and all of that is described in terms of trigonometry because it's all related to that angle and the angles between the velocity vector, the gravity vector, and the acceleration vector. And so useful in physics all the time. Now, finally, the connection to math itself. There's an interesting connection to circles. And so here's an example where I connect trigonometry to a circle. So here I have what's called a unit circle. It's a circle with a radius of 1. That's why it's called a unit circle. And here I have an angle, theta. And so it turns out that this height right here, y, that's this y, is given by the sine of this angle. X, which is this distance here, is equal to cosine theta. It's like it right here. Y equals sine theta, and x equals cosine theta. So if I have a point here on a unit circle and I want to know how high that point is or how far out that point is, I just say the height, y, equals sine theta, and x equals cosine theta. So these trigonometric functions, sine, abbreviated here as sin, but it's really sine, and cosine, writing that out, cosine, tell me if I'm given the angle, what it tells me what this length is, and if I'm given the angle, I can figure out what this length is. And so that's how they're related. Now, what's interesting is if you go over here and you say, I'm showing this for one angle. Suppose I start at a really shallow angle, and I keep increasing that angle. What does that look like? So if I have an angle of 0, obviously the height is 0. That's right here. And as I go around, the height goes up. That's this, this, this. But then I reach the top. And then as I keep going around the circle, the height, this height, will tend to drop. Okay, and that's these points. So I can actually make a graph of what it looks like as I go around. Now let me clear that and do the other one. If I do the length, this distance when I'm at 0 angle right here is obviously 1 because it's a unit circle. And then as I go around, obviously this distance is shrinking. So this goes down. Okay, and then remember that that's the cosine. So if I plot all of that out, you can see that you get curves that actually look like this. And so here I'm actually just plotting it out for the sine, the cosine, and this other function called tangent, which is the sine function divided by the cosine function. And you can see how they go around. And one of the things that you can immediately see when you connect triangles to circles through this unit circle, of which there'll be a video about later, one of the first things you see that's really important is the fact that these functions are what are called periodic. Periodic, there it is. Periodic. In other words, they just keep repeating over and over. And the reason for that is because the sine and cosine are related to a circle, and as I go around and around and around again, I just keep repeating myself over and over again. Now, why is that important? Periodic functions are really useful for describing a lot of things in nature, like waves. Like, for example, here are the waves that are like ripples on this pool, and if you look at those, they kind of look like sine and cosine waves propagating out. Another example are the colors of the rainbow, the light. We can understand the different colors of light as being different frequencies, which means different sines and cosines that are varying faster or slower. In music, for example, the tones of the music, the notes of the music correspond to specific wave vibrations on the strings of an instrument. Like here is a piano. Here's a good project for you. If you happen to have a phone that has a camera, you can stick your camera inside of a piano, or what I've done here is I've stuck it inside a guitar, and I said, let's look at the vibrations and look at the periodic structures that are on the strings of the guitar. And so, sorry, the guitar is a little bit out of tune, but you can see here I'm just putting my iPhone inside my guitar, and I can get these periodic structures that show the vibrations on the strings. So, very important. Okay, so now let's review. Let's think about what we did. Trigonometry, one of the most interesting and useful parts of mathematics. You can see it basically connects to almost anything that you can think about, from the work that astronauts are doing to what happens in factories to understanding things in math. It's a simple concept. It comes from just looking at triangles and measuring different properties of them. And it's sort of amazing that those two simple concepts can have such a big impact in our world. Trigonometry is built around three-sided shapes that are called triangles, and we want to understand the properties of all these shapes. So one of the things that we've looked at is, in particular, are some of the rules that people use. We looked at rules that apply to right triangles, like the Pythagorean theorem, and similar triangles, and how to use that to measure height, for example. People have been using trigonometry for thousands of years, and it's still used every day today. It'll always be used because it's a fundamental property, a fundamental understanding of the way we describe so many things around us. And eventually it connects to other types of math that you'll learn, like geometry, and in particular other subjects where you'll study waves, like especially if you learn any part of engineering, any part of physics, you really want to understand things like music. You're going to always be starting with trigonometry. So here's a quiz. I'm not going to go through this right now, but you can pause the video and you can read these things and think about them. This is a quiz completely for your benefit, so come back to this later, and this is an open video quiz, so think about these things, think about what they mean, go back and watch the video, look up the answers if you want to. That would be great, and this will just help cement all the ideas before you actually get around to learning actual details of trigonometry. So what should you do next? The next video in this series that's probably worth watching after this one is the one that's called triangles, which then starts to talk about details of different types of triangles. It's probably worth watching this video again, because once you start getting into the details of triangles, you're going to start to forget, why am I doing this? Well, watch this video as many times as you want so that you can keep re-exciting yourself of why this is an exciting topic to learn. Then probably a good thing to do would be to watch, after triangles, the unit circle. That is such an important concept. There's a whole video just devoted to that. And then probably go back and watch the triangles one again. And the reason for that is the unit circle is a very focused topic, and it's important to go back and watch the triangles one again to remember all the definitions of different triangles that are not covered by the unit circle. So you might start thinking that, you know, the unit circles, as important as it is for a very specific set of triangles. And so go back and watch the triangles one again. It's good to watch all these videos multiple times to really cement the ideas. Okay, and so with that, thank you for being here, and we'll see you at a later video here on New Planet School.